You finally find the perfect piece of art online. On your tablet, the colors are rich and vibrant, but when the actual canvas arrives and you hang it on your wall, it looks entirely different. It's muddy, dull, and entirely underwhelming. The immediate instinct is to blame the photography, or perhaps the color calibration of your screen. We tend to assume that color is a physical, objective property, something baked permanently into the chemical makeup of the paint itself. But that assumption is entirely backward. Color is not a permanent feature of a physical object. It is a real-time event. This diagram illustrates exactly how that event occurs. Every color you experience is a strict, ongoing negotiation between three distinct variables: a specific light source, a physical object that reflects that light, and a biological observer to receive it. Because color depends entirely on this fragile triad, it exists in a constant state of flux. If you change the lighting, swap the object, or substitute the observer, the original color you saw ceases to exist. The disconnect between buying art online and hanging it in your home starts with a major clash of physics. The device you are holding right now builds colors using additive, emissive light, mixing red, green, and blue pixels. A physical canvas relies on subtractive pigments, which absorb certain wavelengths of light and scatter others. These two physical systems do not overlap perfectly. The mathematical boundary of what a screen can actually reproduce is restricted by something called the gamut gap. Look at this color gamut chart mapping the differences. The wide outer boundary represents the full spectrum of physical pigments, while the much smaller triangle in the center is the standard digital sRGB space. Research shows that roughly 30 to 40% of traditional artist pigments fall entirely outside that digital boundary. Certain chemical mixtures, like vibrant cobalts or deep cadmium reds, are mathematically impossible for your tablet to display. The screen is forced to approximate them with whatever colors it has available inside the triangle. The deception goes beyond missing colors. Physical art owes much of its richness to its surface refractive index. Thick applications of oil paint create a varied topography of imposter ridges and microscopic shadows. A static digital image compresses all of those microshadows into a completely flat plane. By stripping away those physical textures and chemical realities, your digital screen is presenting a highly compressed fiction of the actual artwork. That explains the screen's limitations, but it leaves us with a lingering question. Why does the painting still look off when you finally stand in front of it in your living room? The culprit here is an environmental phenomenon known as metamerism. Metamerism dictates how chemical compositions react to the unique spectral power distribution of different light sources. Because of this, two colors can appear to match perfectly under one specific light, but clash wildly the moment that light changes. An artist usually paints in a studio flooded with 5600 Kelvin daylight, a cool light that brings out crisp blues and neutral tones. But high-end residential interiors typically use incandescent bulbs, emitting a warm 2700 Kelvin glow, which drastically alters how the paint reflects back at you. The physical painting has no fixed, true color of its own. Its appearance is entirely at the mercy of the exact wavelengths bouncing around your specific room. The final variable in the color triad is you. Once those specific wavelengths of light bounce off the canvas, they enter your eye through the cornea and hit the retina. Your biological hardware takes over from there. You have 120 million receptor cells, called rods, to process light and dark, and 6 million cones that process the visible spectrum, operating strictly between 380 and 740 nanometers. Working together, those receptors give a person with typical vision the ability to distinguish anywhere from 2.3 million to 10 million distinct colors. But the final rendering of those millions of colors doesn't happen in the eye, it happens in the brain. And fascinatingly, that cognitive rendering process is governed by the vocabulary of your mother tongue. This split-screen visualization tracks the processing speeds observed in a recent bilingual study. The Lithuanian language has two entirely distinct words for light blue and dark blue, while Norwegian uses only one. The data shows that the Lithuanian speakers physically process and categorize shades of blue faster than the Norwegian speakers. Our biology and our language actively hack the sensory input coming in from the outside world. We do not operate like universal, objective cameras recording the universe. When you look at that painting on your living room wall and the colors seem a bit muted, you aren't looking at a mistake. You are experiencing a highly localized, real-time miracle. No digital screen can replicate it. The physics of flat, emissive pixels will always fail to translate the deep chemistry and textured surface of physical pigments. Even more remarkably, you can't guarantee that the person standing right next to you is experiencing the exact same painting. Their biological hardware and their vocabulary act as invisible filters, building a unique image in their mind. Color is not an objective truth resting quietly on a canvas. It is an irreproducible, highly personalized construction of your own mind.